Hello, everybody, and welcome. My name is Scot Manna with Automotive Seminars, and today I'm going to walk you through a case study and talk a little bit about a diagnostic process on an intermittent cranking no start on a 2006 BMW 330 Ci. We're going to kind of jump right in here. I can tell you that on the screen, as you're seeing, and we're going to be working on a vehicle that's got an M54, according to BMW's acronyms, M like Mary, 54 inline six-cylinder engine. We got a couple of goals that I'd like to walk through quickly before I dive into the car. And I'd like to illustrate using this case study pretty much a step-by-step process to get to the root cause of a problem without doing unnecessary component replacements or swapping things around. One of the things that I really don't like to do as a technician is kind of do diagnostics by process of elimination. I'm more of a testing guy, and I want to have a good process that leads me on a a path to the problem and doesn't kind of send me off. And you'll see what I mean by that as we start to go through this case study, because we're gonna talk about a couple of things that really are part of the diagnosis, but are not part of the problem on the car. Okay, they're not what's wrong. The second thing I kind of want to do with this case study is show you whether or not you have access to it, kind of show you the power that a factory level scan tool has when it has integrated service information in it. And BMW's ISTA scan tool platform has integrated service information. And this is a tool, and there are other manufacturers that have this, such as Volkswagen with its guided fault finding. BMW's ISTA can perform a test plan or generate a procedure that walks you through the diagnosis for codes that are generated by modules that are on the car. So we'll see how that kind of works. We'll view some of that and whether, in some cases it gets you right to the root cause of the fault, or it may kind of take you off on a path that might not be right. So we want to make sure that we keep our minds open and we are light on our feet and are able to follow our knowledge, our skill, and our experience to stay on path to find the root cause of a problem. And last but not least, as many of you who've probably seen me before know, I'm pretty much a labscope guy, and I think a labscope is invaluable in determining problems like this no-start diagnostic. So I'll kind of show you how quickly the labscope kind of pinpoints the exact fault on this car. So let's kind of dive in. The picture on the screen is the engine compartment of this 2006 BMW. This is the M54 engine. It is an inline 3-liter six-cylinder. It has port fuel injection, and it has dual cam phasing or dual vanos, but it does not have Valvetronic. Okay, it is a non-Valvetronic car. So the issue that the shop that's working on this car has is they tell me the engine starts normally, sometimes 4, 5, 6 times in a row, but then all of a sudden will become a cranking no start. It will crank and not start. When I arrive at the shop to help them, luckily for me, the engine's in no start mode right now. It's not starting up, and that just means I'll have a little bit less time trying to wait to verify, or get the problem to happen. The shop told me that there were no codes stored, but when the car doesn't start, when it cranks and doesn't start, they're confident that it has ignition operation and it has fuel pressure. So I'm going to put that in the back of my mind. I'm going to take that with a grain of salt. I might have to verify that. I don't know that yet, but it's a good shop, and I'm sure that they, have no problem determining if those things are working. Again, this is an M54 motor. I'm going to connect my laptop that has ISTA software on it, and I'm going to do what's called a complete test. Excuse me. When ISTA does a complete test, it queries all the modules on the buses on the car and will display all the codes that are stored in a particular car. Once that is done, this software can then calculate a test plan, kind of what I'm looking at right down here. Okay. So I'm just going to have to press a button, and immediately I won't have to leave my scan tool laptop and go to a service information platform like Mitchell or ALLDATA. The directions to perform tests for a given code will be part of the ISTA software. You'll notice I say on the bottom that the test plan does not seem to be directing me quite in the right direction. And you'll see what I mean kind of when we get there. So I'm going to kind of show you this screen and explain it to you kind of quickly, that this is what we would call a topology screen or a network topology screen. And it kind of shows all the modules as how they're laid out in the network. And I have highlighted two. I have highlighted the icon over here that says DME, which stands for Digital Motor Electronics. That's the engine control module. And then I've also highlighted this module icon over here called EWS, which is Electronic Immobilizer System. The W stands for a German word that I can't even pronounce, but I did look it up. But it's the immobilizer module. And you'll notice I have a blue arrow kind of connecting them together. And anybody who's been working on late model cars knows and understands the fact that cars that have passive immobilizer systems, the engine control computer and the immobilizer module on the car have to be able to communicate to allow the car to start. Okay, that's how theft works. Okay, so we have to keep in mind right off the bat that there is there has to be a means of communication between these two modules. And you'll notice that if I kind of circle the modules on the right-hand side of the screen here, okay, these modules are all connected with a thick black line that the software illustrates is the FCAN or fast CAN network. Those modules are all connected together with a 500 kilobyte per second fast CAN system. But the immobilizer module is not on that bus. The immobilizer module is on the K bus, a dedicated body bus that BMW has. So in order for the immobilizer module to communicate to the engine control module, it's going to do it through a gateway. That is this combi or instrument cluster module up at the top. Okay, that is the gateway here that allows communication to take place. So I'm going to come down here and display my fault code memory, and we are seeing sequential screens. So when I tell you that I go to something and I press a button like this calculate test plan down here, the next screen that you will see in this presentation will be the screen that was displayed. So if you remember, the shop mentioned that they said there were no codes stored on the car, but we with this tool have queried every module on the car, and in fact there are 17 fault codes displayed. They are more than what fits this screen. So I'm going to take this scroll bar right here and I'm going to scroll down on this screen and display the next screen. And I have boxed out in red here 4 DTCs that are related to the DME, the engine control module. And that's really all I'm concerned with. I'm here to deal with an engine that cranks and does not start. So I'm not too concerned with codes and other modules, unless of course it was an immobilizer module. But I'm going to go through each one of these codes, and you'll notice that I have 2 blue arrows here. And the blue arrows kind of signify that those 2 codes really capture my attention. So the first one listed is a 2747, which is a misfire for cylinder number 4. Okay, something I note, but certainly not something that should cause a no start condition. The next code is a 27A4, and that is an interface between the EWS3, the immobilizer module, and the DME. And that is a very interesting code. I'm going to have to investigate that. The third one I see is a 281D, which is a BSD, which stands for bit serial data, which is BMW's term for kind of a LIN bus, a dedicated communication line between the generator on the car and the engine control computer. And again, if there was a charging system concern, a battery concern, I'd be interested in this, but this is a crank no start. So I'm not too interested in that. And lastly, I have a 3C1D, and that is a crankshaft sensor signal. So again, I'm interested in that. So when I look at the screen and I look at the 4 codes in my engine control computer, I can say with certainty that the interface between the EWS and the DME could cause a no start, and a non-functioning crank sensor could cause a crank no start. Okay, but there's other background information that makes me wonder about those. So again, I'm gonna use the tool and let the tool see how much help it can give me. So down here, boxed out in red, I'm gonna hit calculate test plan, and I'm gonna get this screen. This screen is going to list what are called ABLs. and you can see that, that's right here. That is an acronym that BMW uses that stands for a procedure. It's going to list a procedure. And for the various codes that were stored in all the modules, there can be a procedure to test that out. For the RPA button, for the crank sensor, for the misfire code. Again, I'm going to focus on where my big blue area is. I'm going to focus on the procedure for the interface for the immobilizer. I want to see that because I want to know, could this be an immobilizer problem? So we're going to chase that down. Again, I'm going to come down here to the lower right-hand corner, and I'm going to click with my mouse this button that says display, and it's going to display my test plan. Now, as you've probably noticed, this software, this ISTA software, is kind of a split screen design. So our procedure that's listed here is on the left-hand side of the screen. And then on the right-hand side of the screen, there is supporting information that is available through the scan tool. Okay. So you can see that the directions to follow for the test plan will show up under procedure, and then supporting information I can look up over here. So I can immediately go to wiring diagrams to look at wiring diagrams for the immobilizer system, or I can get a functional description. Now, you've already seen what's under the procedure side, and I'm sure you've read it, and it says a fault occurred in the tested function, the interface between the EWS and the DME. But notice my big red arrow says the fault is not currently present. And that's really important to me. I want to understand that because I basically can now kind of question, of these 4 codes that are in this module, how many of them possibly could have been set during testing? That I do not know. But I'm going to continue on. I'm going to hit the next button here to see what the tool has to say. And I can see under procedure, it says possible causes of fault. We could have a data communication problem between the EWS and the DME, a short to ground or a break in the wiring in either the high-speed CAN bus or the K bus on the car. Or we could have a problem with the immobilizer control unit, a voltage supply issue, no power or no ground. I don't know, okay? But remember, it's basically saying that the fault, whatever it saw, is not present at this time. Now, I have a couple of things on the screen that I want to explain. I use PowerPoint to put this box in here, and I want you to think of, on a late model car, there's fundamentally 3 ways that the manufacturer can decide to use to immobilize the car, to prevent the car from starting in case a theft decision was made. And that would be to disable the starter motor so the car can't crank over. We can disable the fuel injection so the car can't run, or we can disable the ignition system. And various manufacturers have used different methods, okay? So it's kind of important from a technician standpoint when we're dealing with a no-start condition to make a determination early on. Is the no-start the fault of not so much the fault, but being caused by the immobilizer? Is the vehicle immobilized? We have to make that decision. And in order to make that decision, we kind of got to know the car and know the system to know, is it a no crank, no start? And does the immobilizer disable the starter? I need to know that because then I might be chasing an immobilizer problem. Or is it a start and stall or a no start due to no fuel or no ignition being enabled by the system? So I've highlighted under this functional description side of the screen, under key identification and start procedure, I've highlighted these 2 bullet points. And I'm going to read them to you. The EWS3 control unit checks the key data to ensure it is correct and only then sends an enable signal to the starter. An enable signal to the starter. So that tends to tell me that there is the possibility that we can immobilize the car and not allow the car to crank. And remember, this is a cranking no start. So I'm going to say that if you were to get into this car with no key at all, you left the key in the garage, and you would try to start the car, of course the car's not going to crank. The immobilizer is not going to see a key in the car. If the key was defective, you dropped it and something broke in the key and the key couldn't communicate, again, the car would not crank. We would disable the starter because the immobilizer module can't determine that there's a proper key in the car. The second bullet point says the EWSD control unit sends a variable code to the ECM, to the DME. There, the variable code is checked against the saved variable code. If they match, the fuel injection is released. So we could have a car that cranks over because we're in the car with a valid key, but we could have some sort of a problem, mismatched parts, a used part installed, something done where the immobilizer codes do not match up, and this car can crank and not start because we're not releasing fuel injection. So a number of things to think about as we move kind of forward in this diagnosis. Okay. And there's also some stuff on the bottom about fault recognition in the control unit. And you'll notice it says interface, i.e. the line to the EWS control unit. In this case, the check is carried out in order to establish whether a signal is received and whether the signal is not subject to excessive interference. Now, again, this is fault recognition in the engine control unit. So remember, the codes that we read, there are no immobilizer module codes. The code that we're looking at for this test plan is stored in the DME. And the DME is monitoring the interface line between the two. So again, you could open up the line of thinking that maybe at some point the battery was getting weak on this car, a battery charger was installed on the car, there was a lot of noise created by an old style battery charger, and it caused interference on the communication lines that set this code. I don't know any of these things. I can't determine any things for certain at this point, but I have to keep them in the back of my mind. Okay. So again, I can hit next, but at that point, there really isn't any farther to go. And the reason that I can't go any farther in the test plan is because the fault was not present at that time. Now, before I dive into further testing in the car, I wanted to be able to show you on this wiring diagram that the starter motor, this is out of all data, the starter motor down here, the solenoid in the starter motor is energized or supplied 12 volts by the immobilizer module. Doesn't come from a fuse box or a relay. It actually comes from the immobilizer module. Okay, so that's the module that has to energize the starter, and we know it's energizing the starter. So we have to assume that it's functioning, it has power and ground, and it's seeing a key that it recognizes, and it's releasing or enabling the start, or the crank, I should say. So again, if we review the test plan and review where we have, where we've gone so far, the EWS to DME interface test plan does not show a fault right now. The fault is not currently present. The misfire and the generator signals codes are not going to cause a no start. I don't need to worry about chasing those at this point. The crank sensor, in my opinion, from what I'm told, but I will verify this, appears to be working because the shop said the car had spark. Now, I have a scan tool connected up and I can read data out of the DME. And of course, I'm going to do that before I proceed too much farther into testing. So I go into the DME data, and I'll show you that in a moment, and I take a look at a couple of data PIDs, engine RPM and injector command while the engine's cranking, and they look okay. So I'll show you that. This screen capture was taken while the engine was cranking over, and we can see there was 192 RPM indicated. Engine was cranking over at that speed. And the duration of injection, or the commanded injector on time, was just under 20 milliseconds. Now that all sounds pretty much normal to me. So it tends to say that the engine control computer is trying to start the car, at least in my opinion. So what can we do next? At this stage of the game, I'm kind of at the point where I think I've gone as far pretty much as the scan tool can take me. The scan tool cannot perform under the hood pinpoint tests and tell me if there's actually power reaching certain components or things of that nature. So for that, I'm going to have to default to a scope. And I have a 4-channel Pico scope, and I'm going to connect the scope up to the car as follows. Channel A is going to be connected to the control wire for the number 1 ignition coil. It's fundamentally a 2-wire coil with a dedicated ground. So there's 3 wires in the connector, but it's fed 12 volts, and then a line comes back out and goes to the engine control computer to turn the coil on and off. And that's the line I'm going to be on. And on that line, I'm going to get a primary voltage waveform. Channel B will be connected to the crank sensor. Channel C will be connected to the intake camshaft sensor. And channel D is going to have a current probe installed, and I'm going to connect that current probe to all 6 of the control wires for the 6 fuel injectors. Okay. And it's not a difficult thing to do on this particular car. It was pretty easy to identify. Now, before I leave the screen, I want you to notice one thing that I've put up here, and I've typed in at the end of each of my scope connections, computer output or computer input. And I can tell you that BMW spends a lot of time in their training talking about a concept called IPO. And IPO means input, process, output. And it's fundamentally what all computers do. Okay, they take an input, they look at that input and process it through their operating software, and then they generate an output. So in the case of a cranking no start like this BMW, there are some primary inputs that the computer would want to look at, and that is rotation sensors. Is the engine actually turning over? Is it rotating? So I've got 2 of the primary rotation sensors captured on my scope, the crank sensor and the intake cam sensor. And then it generates outputs, and the outputs would be turn the ignition coils on and off and turn the fuel injectors on and off, of course, at the right time to start the engine. So I'm kind of taking this IPO concept and putting it together on my scope. And before I show you the first scope capture I capture, I'm going to clear the codes on the car. We're going to get rid of all the codes, so you can see I'm clearing the codes on the car, and then I'll show you my connection screen so you understand where I'm at underneath the car. So up at the top up here, you can see I have a BMW iCom, the device that my scan tool interface connected into the OBD2 connector, and the yellow cable connected back to my laptop. And then there's what BMW refers to as the E-box underneath the cowl, right below the driver's side wiper. And you can see my scope connections. So I have my red wire here connected to the yellow wire that I ID'd as the crank sensor, going down to the engine control computer, which is kind of hidden underneath my current probe. I have my green probe connected to another yellow wire that's the intake cam sensor. And then I've got my current probe here, and you can see I've got a bundle of 6 wires in the jaw of the current probe. They're all in the current probe, and they all go to one kind of dedicated injector control connector. So again, using service information or using a wire diagram was kind of easy to connect this up. It wasn't really difficult to get here. Everything is centrally located. It's easy to go here because trying to get to the crank sensor installed on the engine would be much, much more difficult. So it's much easier to go here. And then I crank the car over. And this is the first waveform that we capture. And I'm going to walk you through it. This is kind of my zoomed out view. I have a lot of time on the screen. I was at 2 seconds per division. So I have 20 seconds of time across the screen. So I'm going to kind of zoom into that. And we can see that there was noise generated on the signals. I'm not concerned about that. Of course, that's very common when we're connected into the ignition system on a car. But I'm going to walk us through the scope pattern from the bottom to the top. The blue channel on bottom is my scope lead connected to the number 1 ignition coil. And that looks normal. The scale is in kilovolts. And I'm producing about, I would say, 300 to 350 volts. It is a multi-strike system on this car, so there's multiple firing lines seen during cranking and at idle. That's normal. And you kind of see I've zoomed in, so I have 2 complete revolutions of the crankshaft, 720 degrees of rotation from here all the way over to here. Okay, and in that 720 degrees of rotation, all the ignition coils should fire and all the fuel injectors should fire. Above that waveform in red is the crank sensor. And it looks pretty good to me. It's a 0 to 5 volt signal, as it should be. It has the right amplitude. Everything kind of looks okay there. We can see our missing tooth spot. It's a 60 minus 2 tooth reluctor, and it looks normal. Above that in green is my intake cam sensor. And that is another 0, right here, my 0 line for the green channel, to 5 volt signal. Normal voltage amplitude, it looks fine. And then up on top in gold is my current probe waveform, channel D. And really all I see is the noise that's generated by the firing of the ignition coils. You know, that's an ignition coil firing, that's an ignition coil firing, that's one, and that's one. So I can see that, but I see nothing else. And certainly I'm expecting to see something, and I'll draw it in for you. What I'm expecting to see up here is kind of a current ramp going up to about 1 amp and then coming straight back down. And I expect to see 6 of them. Okay. I expect to see this happening 6 times across the scale, and I see nothing. Flat line. Okay. So I know now, I'm confident, I understand why the car is not starting. It's not starting because it doesn't have fuel. It can have fuel pressure, but we're not actually opening the fuel injector to put fuel into the cylinder. Okay. So we could ask ourselves that we remember that the immobilizer system said that it releases the fuel injection. And I could ask myself, did the car immobilize again? It's for some reason the car in being immobilized and we're not firing the fuel injectors. Or remember that current shows us the integrity of an electrical circuit, but there can be no current flow if the circuit is not supplied with voltage and a ground. And we don't know that yet. We haven't verified that yet. So that's clearly something I'm going to have to take into consideration as I move forward. So that's just another tighter zoom in on it. I'm going to, look at that waveform and give you an analysis that A, channel A is good. The ignition coil is firing. Channel B looks good. The crank sensor is there. Channel C looks good. The intake cam sensor is there. The signal looks fine. Channel D is our problem. There's no current activity. I want to mention at this point that after several start attempts were made where the car did not start, we went back and read codes. No codes were stored in the DME. So as far as the engine control computer was concerned, it's happy. It's okay with what's going on right now. Okay. I believe it's trying to start the car. So what could cause this? Well, I think it's clear that I have to move my test lead. I have to take my scope lead and move it. I'm going to take it off the cam sensor because I don't see anything wrong with the cam sensor. And I'm going to put it on the feed side of the number one injector because I want to see what the supply voltage is to the fuel injectors. A logical next step, I'm going to do the same thing, crank the car over and capture it. And again, I will zoom in on it. And the waveform is very telling. What I see is very telling, very interesting. We've already talked about channel A and channel B, our two, our ignition coil and our crank sensor. Channel C is the feed to the fuel injectors. So I'm connected on the 12-volt side, the feed side of the number one fuel injector. And I can see there's activity. And I see the circuit being pulled low to ground. There's the 0-volt ground line for channel C. And I see 6 of them. All 6 are being turned on. And I can tell that they're being turned on for a specific period of time. But I can also tell something else when I bring a cursor onto the screen. Okay. If I look at my voltage scale over here, I'm on a plus or minus 100-volt scale because normally I would have a voltage spike generated by a fuel injector when the injector shut off. So when I bring my cursor down and I measure the supplied voltage to the fuel injector, my measurement's extremely low, 4.5 volts. What you can, hopefully you ask, what should it be? And of course the answer is system voltage at the time that I'm cranking the car. So unless the engine was barely cranking over, because the battery was very weak, and that's not the case, system voltage while cranking on this car was probably between 10.5 and 11 volts. I'm nowhere near that. I'm less than half that. So we definitely have a problem. The problem being we have a lack of supply voltage to our fuel injectors. The injectors are being commanded. And if I put on measurement cursors for my on time here, when that circuit is pulled low to ground, I can measure it. It's 19.9 milliseconds. And sure enough, if we go back and look at the scan tool, during a crank, 19.86 milliseconds was the commanded injector on time. So our problem is a low voltage supply to the fuel injector circuit. And the scope has made that very clear. So now I can kind of head back to my scan tool and use the service information side of it to try and focus and localize where the problem is on this. And I do a text search on fuel injectors and I find the injector circuit diagram and I find out that there is a fuse and a relay that powers up the fuel injectors. Very important. So I'll show you kind of how I did it, what was done. Again, under a text search, I search fuel injectors and I pull up a whole bunch of documents. There's all kinds of documents populate from test plans to functional descriptions to wiring diagrams. And in the ISTA software, a wiring diagram is denoted as an SSP. So you can see we're looking at SSP 17895, the fuel injector circuit. Okay? That's what I have displayed on the screen. And we can see that there's a 30 amp fuse F5, supplying 12 volts to a relay for the fuel injectors. The fuel injector relay is powered by the DME, by the engine control module. It sends 12 volts into the coil. The coil is hardwired to ground. So I can kind of say at this point that my problem is somewhere between here and here. I don't know what yet, but I have a strong suspicion of what the problem is. If I look at probabilities, what's most likely, the most likely thing, because it's a mechanical component, is going to be the relay. But I don't know that yet. I could have a voltage drop anywhere in the circuit. And I kind of drew in on here where, how my scope was connected up. You can see how channel C of my picoscope was connected right to the supply wire of the number one fuel injector. So I'm going to use the power of this scan tool and what are called hyperlinks, because I don't know exactly where these components are. So I'm going to show you that if I click on this blue hyperlink X6327, it'll pop up on the split screen side of the display exactly where that device is located. And we can see X6327 is a relay that's right here, right in the E-box, kind of right where my test connections already are. And likewise, I can click on this fuse, okay, where this fuse is located, this X8680, and I can see that there is a fuse carrier with fuses inside of it, also right next to there. So everything's actually kind of amazingly centrally located and easy to get to. So the first thing we do is I go to the fuse and I look at the fuse, and the fuse is good. The fuse has got power on each side, battery voltage on each side. The injector relay is removed to test it, and I don't have one. I don't have with me one of my my relay test jumpers that I can like a little breakout device. Okay, so I can't really use that. And the wiring is kind of a pain to get to because the relay is plugged into a socket. The relay appears to be a standard ISO relay, but the pin layout is not standard. The pin layout does not follow the convention of an ISO relay. But the first thing I want to do, because I've got the relay out in my hand, is take a look at the resistance of the coil, the control side of the relay. And I measure that circuit resistance. So I'll show you what I mean about this relay in a moment. Here's the fuel injection relay. And here's the fuse carrier, and fuse 5 is like right here. It's this 30 amp fuse, okay? So this relay is removed, and a standard ISO relay is laid out like this illustration right here. The coil side of the relay are terminals 85 and 86, and the coil would be wired in between those. And then the contact side of the relay goes from 87 to 30, okay? But when I look at the relay that came out of the car, the terminal 30 is not directly across from terminal 87. It's over here, okay, they're on the side. And terminals 85 and 86 are not directly across. They're next to one another here. So it doesn't follow the standard relay convention, but that's okay. It's not a problem. I take an ohmmeter and I measure the resistance of the coil. And I would be expecting a value of somewhere between probably 25 to 80 ohms, something in that range, okay? And I get a much higher reading. I get 560 ohms, okay? So I immediately know that that's a number that is awful close to what I would think if there was a spike suppression resistor in this relay, something along that lines, but it's certainly not the coil. So I think the coil is higher. I think there's something going on with the resistance of the relay coil. And I could test this in the car as well. I got the same reading when I tested it in the car. So the relay coil could be open or it could have high resistance. If there's high resistance in the relay coil, then the strength of the magnetic field that the relay creates will be weaker. Okay. And that could be that could be a problem with bringing the contacts together and not having a voltage drop across the contacts. So just to cut to the chase and get to the fault, a jumper wire is installed. And again, the jumper wire is installed between terminals 30 and 87 of the relay. Those two terminals are jumpered, the car starts, and it continues to start. Time after time, it starts, it starts, it starts. Okay. After some searching on some parts house softwares, we found that Napa has a relay available. It's an AR6282 that matches this fuel injection relay for this BMW. And of course, that was ordered. And I'll just tell you that, that fixed the car. And just to understand what we were looking at when we measured that relay coil, there's a website that you can go to. It's called www.digikey.com. And in this website, you can read the bands. It's got a calculator for color bands on a resistor. So I removed the top of the cover of the resistor, of the relay, and I looked at the resistor and I read the color bands on the resistor. And they were green, blue, black, black, and brown. And when I put those colors into the calculator and I hit search, it tells you what the resistance of that resistor should be. No shock here that it's 560 ohms, exactly what I measured. So it's clear that this relay has failed, and it's failed on the coil side, and there could also be some burning or some pitting on the contact side of the relay. But clearly there's not a strong enough magnetic field to pull this relay down tight and give us full supply voltage to the fuel injectors. With the circuit fixed, I wanted to close this out by showing you, what a normal start or run waveform would look like. So again, we have our ignition coils, and here the car is running. We have our crank sensor, then our supply voltage to our fuel injector, and lastly, our current waveform for the fuel injectors up on top. And we can see that the voltage being supplied to the circuit is indeed charging system voltage, 13.7 volts, exactly what I would expect. It would be, under, 11 volts or maybe slightly less during cranking, but nowhere near 4 volts, And here I just took filters in Pico and cleaned up the waveform so you could get, a pretty good look at what this looks like when it's all said and done. So I'm going to wrap this up. Again, this is the relay that was put into the car to fix the car, and kind of go through our summary. I think I hopefully illustrated a logical process that I kind of went through to get to the root cause of the problem on this car. And I think it's really important that we understand, we have a good understanding of how the system works so that we don't end up chasing or going down that rabbit hole, going down the wrong path. It could have been very easy if we didn't really understand how this car worked and what was going on, that we could have chased an immobilizer system, and maybe we're doing a lot of immobilizer system testing when it had nothing to do with what was wrong with the car. And finally, you kind of can see the importance of good service information, factory service information in this particular case, because we have the ISTA scan tool, and performing our testing strategies in a systematic way to get a correct diagnosis. I want to thank all of you for joining me today and sitting in on this presentation. And I want to say that, without our customers at Automotive Seminars, we wouldn't be able to supply this type of information. I'd like to ask you to like this video if you're watching this video on our YouTube channel. And please, if you're interested in more training, more content on system diagnostics, electrical systems, or individual systems on cars, please visit our website at www.automotiveseminars.com. And there's quite a bit of class material and training material available there. And of course, there will be more case studies posted as time goes on. So again, thank you and have a great rest of your day.